I'm Jerome Buire, so I'm associate professor at Grenoble DNP. So I'm also a researcher of the CRL team, so so electrical grid team of the lab D2E lab. And today we will speak about the electrical grid stability and about the shift from machine stability, so AC grid, to power electronics stability, so mainly DC grid. Actually, I divide my presentation in three parts. So first, I will introduce what is the stability in the grid, and I will explain the meaning of the reduction of the inertia and the impact of the stability. Also, I will focus on new dynamics, which is in the grid, and it is an opening to the DC grid, my second part. First, to explain what is the stability. The stability of a system is its ability to remain functional and balanced in the face of a disturbance, returning rapidly to its normal states. And globally, it is clearly mandatory for the electrical grid. Typically, if we adapt the consumption, if we modify the production, if we have short circuits, the grid have to absorb this perturbation and go back to the stability. To introduce that, I present here a use case. So we have 8 uncontrollable renewable energy, renewable plants, and 9 controllable power plants. First, I want to explain why we want to push the renewable energy in the grid. So the renewable energy have been studied in terms of costs, and it is clear now the energy costs, the capex and the opex, is typically reducing, and the efficiency is increasing. So globally, renewable energy is cheaper than coal, oil, etc., etc. After that, if we add also ecological objective, clearly we want to add more and more renewable energy to the grid. To explain a little bit more, what are these power plants? First, if we focus on wind farm. Wind farm is a system which works at variable speed. It uses machine. So it creates a three-phase voltage with amplitude and frequency variable. It depends on the wind speed, of course. So globally, there are many variations independently of the grid. About the PV, so the PV works in DC. The voltage is variable also, and actually depends on the solar irradiance. But if we focus on your objective, if you use this energy, we want to extract the maximum power in real time. So every time we want to extract the maximum power. So we need control, we need flexibility, and also we need to be independent of the grid. So that's why usually we follow the grid to extract the maximum available power. And in order to do that, only power electronics can do it. Only power electronics. Because it is flexible, it is precise, accurate, efficient, and cheaper. So clearly, we want to add this equipment. So in parallel, we have controllable power plants, coal, oil, nuclear, hydraulic, etc., as you want. So we send the mechanical power from the shaft to the machine, and it converts in electrical energy. If they are an increasing of the load, of course, we will unbalance the energy, so the mechanical power becomes different from the electrical power. So the frequency will decrease. The machine will reduce its speed. So that's why after that we want to manage this balance in order to go back to the stability, to 50 Hertz. So now if we come back to the study case, we will make a load step and the consumption, so we'll unbalance the frequency. So the question is how to manage the stability by the system. In order to compare equivalent case, we will compare for every case 10 power plants, but 1 to 8 renewable resources, and we add the complementary power plant by controllable power plant. So from 10 to 80%. And now, so if we make a load step, so we have made a load step at 3 seconds. We can see the blue curve, which highlights the frequency, which decreases at the beginning, and actually after some tenths of seconds, it goes back to the stability, a little bit less from 50 Hertz, but no problem. But in the case where they are 80% of renewable energy, so uncontrollable system, the frequency go deeper to 49.86 Hertz, and after it go back to the stability. But globally, we can see in the last curve, the phenomenon is completely deeper. It can be dangerous for the machine to modify its speed, because clearly the shaft will absorb this variation. Then if we go to the power plant efforts, when they are 10% of renewable energy, we share the load evolution between all controllable plants. So all of them add only 5% typically of its nominal power. So clearly it is not an issue for many power plants, but if we reduce the number of controllable power plants, we move the efforts to only a small number of power plants. So, for example, in this example, we can see the power can go from 50% to 70%. So it starts to be dangerous for the system, for the power plants. Actually, I have considered this first case, but here we do not consider the line. We have just considered every power plant near the city. Now I will consider the line. So, for example, if we consider distribution grid, the HV grid is modeled as equivalent synchronous machine, and we have two cities, for example. Actually, we can consider PV and batteries, which is modeled as an equivalence of grid-following inverter. So it follows the grid and sends the need power. And actually, we can consider in each city we have a power balance, an energy balance. Typically, maybe the self-consumption. Actually, for now, we push many people to add PVs, to add batteries in house. at home in order to manage the energy need in order to reduce the power need from the system. We consider exactly the same case, but at large scale. For that, so we have modeled the system in state space. So the full system, I don't go deeper in this modelization, but globally the machine, the synchronous machine have 70 states. The grid following inverter have 14 states. Each GFL have 14 states. All networks have 2 states, so typically the 2 currents, etc., etc. We have some inputs, for example, the mechanical power, for example, the solar power, etc., etc. So we model it in state space, and we study the answer. And the modeling of state space, the modeling with state space, is interesting for to understand the stability, because if we study the eigenvalue of the system, we can see directly what is the stability. I don't know if you know this, the state space modeling, but globally, in order to be stable, every eigenvalue have to be in the negative parts of the real parts of eigenvalue have to be negative. So you can see in the I will have a laser, yes. So you can see all modes are in the left side. So it is okay. It is stable. So to continue about that, it is equivalent to say if the state move to the right, it starts to be dangerous. And if it crosses the zero, it becomes unstable. So globally, what we want is all the states are in the left side, typically far from zero, and we want they don't move so much. So it's interesting to have a same stability every time, everywhere, constant behavior. In the vertical axis, you can see the frequency. But if this mode creates an oscillation, you can see the frequency. For example, you can see the 64, 65 mode have the vertical value is 1.5 Hertz. So it is equivalent to say if we made an event in the grid, we can see a frequency of 1.5 Hertz. Actually, the frequency not very important. Maybe it can be dangerous for machine, for equipment, but globally not very important. What is important is don't go to the right. In this study, we have studied the impact of the power sharing between the upstream grid, so the synchronous generator, and the grid flowing converter. For example, sometimes the sun is exactly equal to the load. So the power flow coming from the synchronous generator is equal to 0. It is equivalent to say, in my simulation, the grid following, so the CT, the PV and battery here, produce 0.5 per unit of power. So the synchronous generator sends 0. You can see the mode of that in red in the graph. So typically all modes are the most left parts from these two modes, but you can also see the mode 75 is at the right side. So what is equivalent to say is the mode 64, 65 is more damped, So it is better, excellent, no problem. But for the mode 75, this mode is stable, yes, but go to the instability. So it starts to be dangerous. So be careful with that. Next, if we study the impact of the network parameters, for example, we can modify the line length between the CT and the synchronous generator. It is equivalent to say, if we have a transmission grid with less machine number, with less machine, it is going to say the equivalent upstream machine is far from distribution grid. So clearly in the future we will see that. And now if we study some mode of the system, you can see when the line length is very short, so in blue, you can see all mode is at the left parts. So clearly it is the best possibilities. And I think it is it is easy to understand that. If you are near the machine, it is easier to manage the stability. But if the line is very big, so if we have very long lines, you can see the mode go to the right. Actually, every mode go to the right. So we lost the stability. In order to manage that, many people in the literature propose to use a QV droop in order to manage the voltage. And clearly, this controller is interesting to manage the steady state voltage. And clearly, it works well. But what about the stability? Adding this system adds two more modes, 57, 58. And you can see if we move the main coefficient from 0 to 10, so the droop, the QV droop, you can see if the value is very low, this mode is very stable, perfect. And if it increases, it moves to the left and actually cross the 0 at near 8, at the maximum value of M is 8. Actually, you have exactly the same question for the PF droop of machine. Maybe you have ever seen that. But if we focus on dangerous mode we have seen before, so typically 64, 65, 75. But globally, we can see some modes is moving, yes, but they move just a little bit. It don't move so much. So globally, the stability of the system is not very changing. So it is equivalent to say QV droop actually don't help the stability so much. So it is not a good candidate to manage the stability. So some conclusion about that. About the potential future electrical system. Globally, we reduce the inertia. So the consequence of the machine is a deeper frequency behavior. So it can be dangerous for machine, etc., etc. Maybe we can consider local power flow done by batteries in grid following mode. So what is done for now in many homes. But about the stability, it is important to say the network dynamics have to be included now in the modeling, because we cannot consider machines are near the city, are near with other synchronous machines, etc., etc. So now the network dynamics have to be included. So also mode related to the active power, so start to be dangerous. the question is, can be accepted by system operator. But with the previous system, we have shown the frequency stability is not enough, because in my previous system, clearly, we have not managed the stability. The grid following system has worked, well, the batteries are working grid following, so they don't push the frequency. So the frequency stability is not enough. It is important to add also voltage stability, etc., etc. And actually, the question for that is, maybe the AC system reach its maximum potential. So that's why now I open to the DC. I will explain why. First, if we consider the geographic representation of a distribution grid, so you can see some HVMV substation. You can see AC link, which supply many loads, etc., etc. You can see some wind farm, some solar panel in the grid. Okay. And the question for that is, we can consider here some use case about the DC. First, point to point, so between, for example, two HVMV transformer. Next, we can also consider a multiple connection. So maybe a grid, a DC grid inside the AC grid. It allows to add renewable energy, for example. It can be also MVDC line to connect remote generation and DER to the grid. So typically, if you are far from the AC grid, it can be interesting to extract the energy from a DC link and not for AC link. The last use case can be also a district or campus or a big load, which is totally in DC, so a DC microgrid inside. Now, if we go a little bit deeper inside the DC line, you can see, so here the typical point-to-point topology. So at the left side, you have the AC grid with output filter, the VSC, the voltage source converter, so maybe transistor, diode, etc., etc. In the middle, the MVDC line, and at the right side, the second VSC, so the second converter from DC to AC, and in the point B, the AC line. Inside the system, of course, you have first the physical layer, so the topology, output filter, DC and AC line. You have also the control layer with outer loop, which can manage the power, manage the DC voltage, etc., etc. The current control, etc., etc. What is important here is to understand AC grid is not controllable, but a DC grid is controllable. A DC grid includes a big part of control layer, so it is possible to manage it in real time. Here we have model the system, and we have validate with MATLAB Simulink this system. So typically we have two networks, so network A and network B, and in parallel we have AC grid. So with RA, LA, RB and LB, and in parallel you have two VSC and the MVDC line. Here we can see the output power of the VSC A and the VSC B. You can see here the output power of the VSC A is slower than the power in the point B. So what is important here is the controllability of the system. allow to decouple a little bit the power between 2 points. This possibilities is not, actually it is not possible for AC grid. AC grid, the flow is unidirectional. You cannot manage it. So next, if we consider an expansion of the grid, of the distribution grid. So for example, we have first MVDC line. And the question is, we want to add a PV farm, for example, and we have understood the MVAC line is not enough. So we want to add either MVAC line or MVDC line. So we want to compare the both expansion. And the question is, can we improve, for example, primary frequency response in case of low inertia grid and DER perturbation? Just I go directly to the results. In the case one with the MVAC system, we have seen before, so a big event creates a deeper event about the frequency. But with MVDC, we can see the frequency can be managed clearly better. We have done it without adding inertia, without adding virtual inertia, etc., etc. What is important to know here is the two VSC can manage the power flux between the equivalent grid A and the equivalent grid B. And it is clearly more efficient. So final conclusion about that. So power electronics and low inertia system impose to consider an active behavior of components. Usually with AC grid, with classical equipment, load, the system is a sum of impedance, only impedance. And actually, it is very complicated to manage the grid with impedance, only with impedance. 10 kilometers of line is an impedance, and you cannot manage it. It is impedance, and that's all, finished. So the question for the future is, we need to add an active behavior of system. Clearly, many people work on equipment, of active equipment, so typically VSC, load, active load, etc., etc. Yes, it is very interesting. But about the grid side, DC-link can be a good candidate to add this active behavior. Actually, we can also add AC-AC converter, of course, for that, because if you have converter, all converter you want, it can be interesting to manage the power flow inside that, and clearly it works very well. But actually, if you know a little bit what is inside AC-AC converter, usually it is AC-DC and DC-AC. So just we separate the both converter. We add distance between the both, and it is equivalent to say we have DC-link. Exactly the same. Also, the question is where we put the DC-link in the system. And the proposition I have studied here is to put DC-link near renewable energy and near the load. So we put it in the distribution grid. Clearly, some people work on HVDC or LVDC. So HV is for the transmission, So typically far from the load, but near very big power plants. Or LVDC, so it is exactly the contrary. The DC link is near the load, near the client, but far from the generator. First results have shown DC link can dump easily low frequency behavior. It is clear for that for now. Maybe for the questions, so what we have studied here is, can we handle also high frequency disturbance? And for that, it is not very clear. For that, we have to add some sub frequency, sub behavior in order to manage that. The question also is about large signal events. So typically short circuit, for example. Usually we explain short circuit is very dangerous for power electronics. Actually, it is not. We have to design a system which accepts short circuits. It is necessary to avoid to destroy the system with short circuit. Thank you very much for your listening.
Long live India and France friendship.